Hello, everyone. I am Nirmal Malapaka. Welcome to my talk. I'm a kernel developer in the visualization group. In this talk, I'll show you some of the tabular visualization functions we've been working on. My talk here will focus on visualizing tabular data. So let me begin by giving you an overview of what I will be covering. We will begin by looking at the tabular workflow and where visualizations fit in. Then we will look at the scope of support and coverage for tabular data in visualization functions. Then we will look at the specific syntax we use in various functions to plot tabular data. After that, I will introduce the concept of position encoding, which is the prime focus for tabular support in plots for this upcoming release of the Wolfram language. I'll pick a few datasets in tabular format to illustrate the different syntaxes that can be used to plot columns. I'll highlight how the interpretation of these syntaxes in different plots can lead to different ways of looking at data and understanding them. We will take a quick look at specialized plots like pairwise plots, which have been updated to work with tabular. Then we will look at some charting functions and the different types of positions we can handle with them. And finally, for completeness, I will talk about tabular support in scientific visualization functions and the future directions for this project. Okay, so let's get started. Here is an illustration of a typical workflow for tabular sorts of data. It begins with fetching data from different sources, performing cleaning operations to get the data in a useful state before the process of understanding begins. Understanding typically involves an iterative process of transforming, visualizing, and modeling data to gain insights. And finally, these insights are packaged up and communicated in the form of reports and such to end users who can act on these insights. So in this context, visualization plays a central role in getting insights into data. But also, visualizations are a preferred way to communicate these insights. For this talk, I have chosen examples that can also be used for communication purposes. Features that help more with data analysis will be added in future releases, and I'll mention some of them at the end of this talk. Another thing I'd like to mention is, as you can see, there are quite a few steps in the workflow before we hit visualization. These are not in the scope of this talk, so you will find that the data that I use has been prepared in advance. Some of the other tabular talks that I mentioned will shed more light on these steps if you're interested. Okay, so what is the tabular visualization syntax? To understand this, let's look at the structure of tabular. We have columns that we can think of as variables and rows that we can think of as measurements. There can be different types of columns like categorical, numeric, date, quantity, expression, and so forth. And in each column, we have values of that type or missing values. In terms of coverage, for this release, we are updating around 75% of our visualization functions to support the syntax. I obviously won't go through all of these functions, but I'll pick functions so that I can convey the idea behind how we are approaching this problem. Before I introduce the syntax, let's look at some example tabular data. This is a tabular that contains data on cars. We have columns for manufacturer, model, engine displacement, number of cylinders, type of transmission, along with city and highway mileage. So if we use column keys function, we get the name of the columns. And the syntax we use in visualization looks like this. It is a rule where the left-hand side is the tabular and the right-hand side is the column name. So if we want to select the city mileage column for plotting, we say rule cars city. And this form of the syntax shows that the input tabular has 12 columns, and the city column of numeric type is selected with all 235 rows. We can select two columns in this way using a list on the right-hand side of the rule. Again, we see that both our selected columns are of numeric type. In certain plots, we may want to select multiple sets of columns. And in this case, we can use this form where the right-hand side is a list of lists. Here, automatic means the values of the explicitly selected column will be indexed. Okay, so now we have a way to specify which columns we are interested in visualizing. It so happens there is more than a few ways to map the values to visual elements. For this release, we have decided to focus on mapping the columns to positions in our coordinate system. Let's call this position encoding. So if we look at the two columns we are interested in, namely city and highway mileage, and I'm just picking the first 10 values for this demonstration. As you can see, we map the city column to the x-axis and the highway column to the y-axis to get a list plot. Obviously, when using the syntax, you are going to get the plot of all the values in the column. But you get the idea of how these values are mapped using the syntax. And for multi-syntaxes, you can think of this illustration with multiple columns stacked up for each axis. Let's look at how different plots handle the syntax. Let us take the humble number line plot. Using this syntax, we get a point for every value of city mileage. The same thing with a histogram. Gives us a better idea of the distribution of the values in the column. If we want to get the 5-number summary for the selected column, in addition to the distribution, we can use box whisker chart. We can also use our multi-syntax to compare the distribution of values in the columns. Now let's switch to a different tabular. This one has data related to penguins. So there are measurements for specific penguins, and the columns have information regarding what species the penguin belongs to, what island they're found on, as well as their bill and flipper measurements along with their body mass. So here we are visualizing these data using listplot, and we are plotting the body mass on the x-axis and bill measurements on the y-axis. This is using the multi-syntax, and this creates two groups of points from 3 columns. And here we are using the plot layout option to split the groups into their separate plots. Now, suppose we want to visualize a different aspect of these data, and we want to plot the bill length of the different species. Then we can transform the data to make a tabular like this. Note that the species and bill length columns have disappeared, and now we have columns for each of the species of penguins with their corresponding bill lengths. Now we can use our multi-syntax with index values to create a plot like this. Here, bill lengths are grouped by the species of the penguins. Briefly switching back to cars data, just to show how different plots do the right thing in terms of interpreting the syntax. Smooth histogram gives us the distribution of city and highway mileages, and the density version gives us a single distribution. So I guess you get the hang of the game we are playing here. For position encoding, axes are key. And plots like parallaxis plot provide us with plenty of those. With more axes, we have more flexibility in terms of mapping the columns. So here we are plotting each of the penguin variables onto its own axis. Having said that, more dimensions may not yield more insights into the data. Here it looks like there is some crossing over going on between body mass and bill measurements, but it's not clear. We can try to investigate further by using our multi-syntax and creating groups. We are separating out bill length and bill depth to see if we can discern any patterns. Sometimes, however, things are clear. So here with cars data, one can see a clear pattern linking number of cylinders and mileage. Also, apparently there are some 5-cylinder cars. Sometimes the difference between spotting and missing patterns with position encoding can be something as simple as switching the axis around. And this is something that is built into plots that use position encoding in special ways, like pairwise plots. We introduced pairwise plots in the last release, and in this version, we are extending support for tabular plots to all pairwise plots. I gave a tabular data visualization talk at last year's tech conference where I went into more detail about pairwise plots. I am providing a link to that talk here in this slide, and if you're interested, you can check that out. But here I am recreating one of the plots from that talk, with the only difference being the data and syntax are more tabular friendly. In pairwise plots, every column we select is plotted against every other column, giving us a 2x2 grid of plots. So what about visualizations that either do not use position information directly or have limited capacity to do so? Well, enter charts. Without going into details, charts like less granular data. And one of the ways to get that is by aggregation. Here is some data on industrial output. So we have information about the sector, region, kind of product, quantity, and the related economic metrics. So we want to produce some charts that give us insights into these data. Using a tabular transformation function, we can aggregate the profit, revenue, and cost columns by product using an aggregation function. In this case, we are using the same function for all columns. Okay, now we are ready to use this form of data in our charts. Let's start with a pie chart. We get the inner circle, which is the profit column, and the outer ring, which is the cost column. The chart is colored by product, and the slices represent the values. On the other hand, if we plot the same data using bar chart, we can take advantage of the automatic grouping behavior of bar chart to group profit and cost by product. Then we can make a different comparison of these same data. So we start to see here that the definition of what a position is expanding to incorporate more types of data. Here, x-axis is categorical and y-axis is numeric. But we can go further and use bubble chart to encode 2 categorical positions and 1 numeric position with our industrial data. And this is what that looks like. While we were doing this implicitly in pie chart and bar chart, here we are specifying how to interpret the encoding using scaling functions. So we have products along the x-axis and sectors along the y-axis. And the sizes of the bubbles show the revenue. We can, of course, do that with our list plot as well. And here we have come a full circle. This is essentially the first number line plot we looked at, where all the mileage values were squished down. Here we are able to group them by manufacturer using categorical values as a nominal scale for the y-axis. And that is about categorical types. I just want to briefly mention dates. Usually dates in a column signify some sort of series data being captured. And we have our date plots that can deal with these. When list plot detects a date type, it will automatically switch to using the date scale. This plot shows the life expectancy data from 6 countries over roughly half a century. And we can plot these by selecting the appropriate columns from the tabular data. Okay, just a note about scientific visualization functions. As I mentioned, we support this syntaxes for a large portion of our visualization functions. And these include scientific visualization functions like density plots and slice plots and complex plots and so forth. Even though typically there isn't a whole lot of scientific data out in the wild in tabular formats, if such data are captured, we can still use them. So here I am constructing a tabular with some complex values in one of the columns. And then I can use the same syntax inside complex plot to plot a Julia set. Okay, so future directions. The 25% or so of the visualization functions that do not support tabular syntaxes yet broadly fall into the categories of vector and geoplots. As I've tried to demonstrate in this talk, position encoding isn't always straightforward. And vector and geoplots have their own notions of what a position means. So we need to think carefully how we go about supporting tabular data in these functions. So that is going to be one of the future directions for this project. We are also working on adding more plots that deal with purely categorical data. These are going to be a good match for typical tabular data cases. So these are plots like mosaic and tree maps. Then being able to visualize more dimensions in plots is another area that we're exploring. And what we are doing for this release gives us a solid foundation for us to add additional encodings. The syntaxes I've shown you can be understood at different levels. At the most basic level, they provide a convenient way to extract values from tabular to be used in visualizations. That convenience also extends to the subtle differences in the way plots choose to interpret the syntax. But at its core, this new way of specifying data in visualizations gives us a handle to our data source and site plotting functions. What that allows us to do going forward is to interpret the data in the context of the visualization. And this will give us the ability to automatically encode more dimensions from tabular data sources using visual properties. These typically involve ways to group values based on different criteria, and then mapping them to visual elements like color, shape, size, etc. But more on that in future talks. Once again, thank you for attending, and I hope you have a great rest of the conference.